It's great to be here. You're probably wondering why in a whole 3 days of non-von Neumann architecture, Murat would invite somebody who sort of, spent a lot of time delving into von Neumann. The first thing I would say is I greatly admire John von Neumann, but I don't. When you're someone's biographer, sometimes you write a biography of somebody you really like, and as much as I have learned to admire John von Neumann, I can't say I really like him, but I have tremendous respect for what he did. So I'm going to use his own words. I'm sort of the token historian in the room, but I was very happy to see in the last couple of days we had quite a few references to history. In some technology audiences, there's almost no attention to history. So I'm glad to see you pay attention to the history of your field. And he's warning us that you need to pay attention or you repeat the same mistakes. So I'm going to just start with, I think, one of the patron saints of your field of neuromorphic computing was Alfred Smee, who in 1850, he published a whole series of books, but in Instinct and Reason, he sort of delves into how to recreate the nervous system. And he, as you guys, he starts with the worm. So I don't know if this is on open worm, but it's 161 years ago. And he arrived at very much the same model, the inputs, the output, the brain, and then that all depends on the feedback loop to the senses to make this work. And then a year earlier, so usually the next question is, well, what about consciousness? And he just nailed the whole consciousness debate. This is all you need. If people can stop, I think, arguing about it, that if an image is produced by an action upon the external senses and it concurs with the action in the brain, the image is then a reality. If an image occurs to the mind without a corresponding simultaneous action of the body, it is called a thought. And the power to distinguish between a thought and a reality is consciousness. And I think that's what you're getting to. We saw in Jeff Hawkins these feed-forward networks that essentially are imagining what's coming next and then matching what they're imagining to what actually does come next. And that's getting on the verge of this sort of definition of where consciousness really comes from on the micro scale. And then we'll jump ahead to I think the other patron saint who just really nailed the problem with AI was Louis Fry Richardson, who is mainly a meteorologist, but his electrical model, so it's a non-deterministic circuit illustrating a mind having a will. So this solves the free will problem, but it's capable of only two ideas. But that doesn't matter. You can, if you put enough of these units together, these sort of non-deterministic transistors, you can get all sorts of interesting behavior. So then all this was developing beautifully. I mean, it was exactly what you're working on about 150 years ago. And then Alan Turing comes along and kind of ruins it with his purely deterministic model of computation. And what he gives us is this marvelous, at the age of 23, this model of the computing machine. And it's universal. Once you have this machine, you can do anything if you have enough machine cycles and enough time. But it's one-dimensional. It's a one-dimensional model. It's very beautiful to a mathematician, but it's of not that much practical use. So von Neumann comes along, who's very well familiar with Turing's work, and always honored Turing by sort of let the whole world be a long paper tape. So he left everything in this linear input-output model, but what he did was he changed the memory. Turing's machine had a one-dimensional memory. You had to go through the whole tape to, like the old tape drives. Von Neumann made the memory two-dimensional. That was an enormous advance. It was such an enormous advance that we've been stuck there for more than 60 years. We've been stuck in this von Neumann two-dimensional address matrix, which he would be horrified that we had named it after him, because for him it was just an approximation to solve an immediate problem. So he came to Princeton, this whole gang of people. They're all Hungarians in the room there except two Americans. And they end up here in New Mexico, 1943, to start the Los Alamos project. His description of arriving there, it's worth meditating about although one should probably not sell one's soul to it. By the way, computers are, as you suspected, quite in demand here too. He's writing to Clary, his wife. Now, computers, he means human computers. They didn't have any, what we would call electronic computers. They had simply IBM electromechanical machines doing the computing work they needed. Now, von Neumann had already a strong interest in the way the brain worked. In order to solve these anomalous problems, he was sent to look at the ENIAC, which was our one American high-speed electronic computer, where even the maintenance manual was restricted at that time. And as soon as he saw the ENIAC, he saw that he sort of put the ENIAC and Turing's ideas together and came up with something different. Now, there's a lot of question of whose ideas he put together. They weren't all his, but he did act sort of as the orchestra conductor who if he couldn't play the violin, he knew where to find a good violin player. So he was out here at Los Alamos with all these people who'd been pure. Stan Ulam had been a pure logician. Feynman was just a theoretical physicist, and suddenly they were given real hardware to play with, and it was intoxicating, and they couldn't go back. So after the war, they all decided, what's the next exciting thing after building this atomic bomb? It was going to be computation. So von Neumann then is listed as the lead author in this report that Todd mentioned, I think, on the first day, the report on the EDVAC. It was sort of a report on what would come next after the ENIAC. And it only has von Neumann's name on it, but if you read it, it really is von Neumann's ideas. He took Eckert and Mauchly's ideas, and actually Hermann Goldstein typed the report, but von Neumann was on these constant travels feeding these ideas back. And the whole thing is done with a as a neuromorphic system. He doesn't use vacuum tubes. He uses McCulloch-Pitt neurons. And partly because at that time the electronic circuits were classified, he couldn't talk about them, but he could freely talk about these sort of abstract neurons. But it's how the whole machine works. So this awful thing we're stuck with, this von Neumann bottleneck and all this stuff, actually came out of a neuromorphic analogy. So there's all the detail of it that's in this report. So all the fundamental processes of binary arithmetic that exist in all our processors were started from these sort of neural schematics of how you could actually do it using these excitatory and inhibitory components. And then we got the central arithmetic unit, the memory, the input-output, and the recording medium. Sort of all what we view as this fundamental von Neumann architecture we've been stuck with. How to build an adder. And you can see even the memory, it has these time delay neurons is how it's seen as being done. Now, how to actually execute the memory was a very interesting problem at that time. There was no solid-state memory. So von Neumann's answer, which is what ended up actually working first, was to use the iconoscope, which was Vladimir Zworykin's idea of effectively a cathode ray tube that writes charged spots of electrons on a tube and then is able to go back and read the state of those charged spots. So effectively it's a matrix of capacitors, a two-dimensional matrix of capacitors on the face of it's an analog device where you are deflecting the electron beam with the amplitude of the voltages. So getting that to work was a horrendous problem of electronic engineering, but it was a brilliant idea. It was someone else's idea. So Willis Ware, who was the last of these original engineers who died just 6 months ago, described, that von Neumann was the person he was there at the right time with the right connections with the right idea, and he had the ability to get the funding. And he moved around a lot. He was constantly traveling. So he's the person who, if he didn't even have the ideas, he distributed other people's ideas until sort of he ended up getting the credit for them. To execute this thing in electronics, he brought in, a gift for finding the right people. He brought in Vladimir Zworykin, who had brought the world color television, also was wondering what next. So the whole thing started in Zworykin's lab, and the idea was to solve the weather prediction problem. This was not seen right away. Actually, it was also for the hydrogen bomb problem, but the public face of it was to solve weather prediction, outline of weather proposal in 1945. In talking to Lewis Strauss, who was the head of the ONR, which was the predecessor of ARPA and DARPA, he made really the same argument. It's the only argument you need to make now that when you say you can do something 10,000 times faster or you can do 10,000 times more, but well, so what? That's no big deal. But that you can, if you can do it that much faster, you can do things that are totally different. And that's the point of neuromorphic computing. You'll be able to do things that just are not able to be run at all in the other way, except with just prohibitive amounts of time. The first meetings are held in Vladimir Zworykin's office at RCA. I think RCA made probably the worst business decision of all time, which was not to support the computing effort. That the future was in television, not computing. So it sort of by default went to IBM. In that first meeting, the commandments are given that the design is modular, which we now see, of course, in chips and cores, that the components are exchangeable. Words coding the orders are handled in the memory just like numbers. The data and the instructions are indistinguishable. Now, how to do a sort of commercially effective memory, RCA's one thing they were going to contribute was the memory tube, this thing called a Selectron, which was a sort of like a dinosaur with feathers. It was going to be an all digital matrix inside a single vacuum tube envelope, 4,000 bits. Functionally, it was like a USB stick. You just plugged it in and you had a 4,000 bit speed of light memory. The problem was they only set 2 people working on it, and it didn't get done in time. So they had to sort of go on without it. But it's why our architecture we have today, in some ways, why it works so well, because it was built expecting the Selectron to plug in as memory. That's why our architecture is so able to scale so well, because we were expecting that kind of memory, and then when we got core memory, the architecture didn't have to be changed. So fundamental things as fundamental as an AND OR gate had to be sort of nailed down. It was all being done with analog, sort of unstable components. You can see they're trying to build a shift register here, but they're talking about it as communicating banks of cells. They still see everything as a network of neuron-like components. That's the actual first shift register they got working. And everything had to be replicated. It was a 40-bit parallel machine, so everything had to be built 40 times. This is shift register number 7. So they went through 6 iterations of a shift register design before finding one that they settled on, and it's the one we're still stuck with today. That's the Selectron that finally did get working, and like IBM, they put their own initials on it. This was only 256-bit memory. It actually ran they used 100 of these in the copy of this machine built at RAND. So back in Princeton, they had no memory, but they had an arithmetic unit, how to get it running. They built this linear memory on its magnetic recording wire going through bicycle wheels. They could get 90,000 bits per second input-output. So that's a 40-bit word. So you're seeing there the moment of transition between the analog world and the digital world, where they're dividing this, sort of the pattern recognition problem to get a 40-bit reproducible word out of that. Then they went to what Neumann's original idea, the cathode ray tube memory, using off-the-shelf oscilloscope tubes, 5-inch tubes. You could get a 32 by 32-bit matrix on the face of the tube with an amplifier built right on the face of the tube, because even if you had to transmit those signals for 6 or 10 inches, enough noise would creep in, you'd start to lose bits. So they did all the processing right, very much what you see in the visual cortex, where you're doing a lot of processing right in the actual layers themselves with very little loss. Tremendous timing problem. The charged spots can hold the memory for milliseconds, but they're going back every 25 microseconds and reading the spots. So for the first time, you have a memory that's operating at the speed of light rather than the speed of sound. So you have 7/10 of a microsecond to make the distinction between what represents a 0 and what represents a 1. So there's a 1,000-bit, a 32 by 32-bit array in each of these 40 tubes, 20 on each side of the machine. So it's built like a V40 diesel engine with memory tubes. Each tube has its own logbooks, which is how we get these photographs. So a photograph like this is not, you're not looking at a representation of bits that are somewhere else. You're actually looking at the bits themselves were pixels on the face of the tube. And then that was transformed. The way sort of biology will flip things around. Then we started using this for display. But it started out being actually the memory of itself. So you could watch. It was very good for debugging. You could go in and actually, this machine had, it was asynchronous. You could do it one instruction at a time and watch the bits moving around. So that's the archetypal photo. Von Neumann had this gift for putting the right people together. Herman Goldstein and Julian Bigelow, who didn't agree on anything and would never work together, they were willing to work together for the sake of von Neumann and Robert Oppenheimer, who helped put the facility and the money together. All the crew of the people who von Neumann was just a very good sort of captain of the ship. One of the crew there is Hewitt Crane, who then went on to develop the Neuristor, which must have been sort of an outcome of his time there. When the machine was revealed, it was called a mechanical brain, which now we look back and think, oh, that was kind of silly, but it was very much the context of the time. Chief engineer was Julian Bigelow, who was co-author of this fundamental paper, Behavior, Purpose, and Teleology, which is the paper that gave rise to something called the Teleology Society, and then that became the cybernetics movement. And in that, Bigelow says that there's no fundamental difference between organisms and machines. We just need to sort of find these fundamental principles that unify them. That led to cybernetics, giant brains. It was very much, that was the paradigm of the time. And William Ross Ashby's Design for a Brain, which is sort of a whole book that's an architect of how to build a working neuromorphic computer. And his law of requisite variety, that a control system must be as complex as the system it controls. And I've paraphrased that into the paradox of mechanical intelligence, that anything complex enough to be intelligent is too complicated to understand, and anything simple enough to be understandable is not complicated enough to be intelligent. But I think you're on the right track, which is building these systems that we understand how to make them sort of impossibly complex and let them run the problem. So lots of people have been working on this a long time. Von Neumann in particular, fortunately von Neumann and Turing both died, tragically young. Now, to do this with unreliable vacuum tubes meant you needed a very different kind of architecture. So we got set back, sort of solid state set us way back, that we suddenly had reliable hardware. This laptop will run billions of cycles for months and never fail. The hardware just doesn't fail. But at that time, the hardware was failing all the time. So von Neumann was looking at this probabilistic logic, which is much more, of course, what the brain does. He looked at this in great detail and was what he was working on when he died. And he came to the conclusion, which is very true, that what you're seeing in the brain, the sort of connections in the network are their own simplest description, that you can't make an abstract description of what's going on. The actual connections themselves are the simplest description of how it operates, and that to understand this, the logic will have to undergo a pseudomorphosis to neurology to a much greater extent than the reverse. And that's still something we stumble over. We keep trying to define this stuff logically when it really, I think we're seeing this in what we're learning here. It really is working better the other way around, to sort of build the hardware and get it to work without necessarily having a full logical description of it. So 1951, they're getting this machine actually running because they have this big problem. They're trying to determine the feasibility of a thermonuclear explosion. That's their mission. So all these other grand things they want to work on have to be put aside to solve this problem for the AEC, which they do. And strangely, Oppenheimer refused to take credit for it. He sort of was outcast as a martyr for opposing the hydrogen bomb, and really he had done as much as anybody else to make it happen, but he wouldn't step up and sort of take credit for that. Von Neumann really had very little working relationship with Oppenheimer. They posed for this picture, but they really worked on nothing together, whereas von Neumann worked intimately with many of the other people out here in New Mexico, particularly Stan Ulam and Nick Metropolis there at the weekly Los Alamos poker game. Nick Metropolis, who ran computing at Los Alamos for the rest of his life and had all sorts of ideas about this same, all these people who worked in the beginning of computing before we got stuck in the von Neumann architecture had a great affection for the sort of non-von Neumann stuff that they had been working on when they were interrupted. That's Nick with the Maniac, the machine at Los Alamos. And here, Bob Richtmeyer is complaining that von Neumann put instructions and data in the same memory, but why does it have to be that way forever? It doesn't, of course. You could do all sorts of computing quite differently. Here they're playing chess against the Los Alamos machine, but if you notice they're cheating. They're playing on a 6x6 board with no bishops, and Ulam called it anti-clerical chess. Now, von Neumann, if you know him for nothing else, you probably know him for Theory of Games and Economic Behavior, this wonderful 682-page book on how a reliable economy can be constructed out of unreliable actors. And he did that book during the war. Then Stan and Johnny they were collaborating on a huge sort of encyclopedic definitive book on the structure of biological and artificial automata. So that was what they were trying to do. It was exactly what we're all trying to do, sort of get some fundamental understanding of nervous systems and computation. But the problem was von Neumann wrote the economics book with Oscar Morgenstern, who was a diligent worker, but he was trying to write this book with Stan Ulam, who was the laziest but most intelligent guy on earth, and they never got any of it done except some outlines. This is one of their outlines. So you can see chapters. Turing, which is everything you can do with a Turing machine. Not Turing, all the stuff that you cannot do with a Turing machine, that somehow biology still does. Pitts, McCulloch, so all these ideas are in there. And Ulam, that's the idea of cellular automata, which really goes back to Ulam more than anybody else. So it was a tragedy. Von Neumann him and Turing both died becoming, the consuming interest was in biology and neurobiology in particular, yet they both died too young to go through with it. So the only way we really have access to John von Neumann's ideas on this are through Julian Bigelow, who worked so intimately with him and did write a few things down later. Here he's explaining that the machine they built, it didn't have a clock. It was just a system of interconnected gates. That's how they saw it. They didn't see it in this sort of Intel way of a clock governing everything. You don't need clocks. There's a difference between a counter and a clock. A clock keeps track of time. You're only keeping track. The reason they have to have a counter is just to keep track of the addresses of what they're doing. Sequence is different from time. No time is there. And that's, of course, the difference in biological computing. You do have time delays in your neurons. So Julian Bigelow, who died in 2003, very bitter at how he was treated. It was a sort of political, institutional issue, but he never wrote another paper in his life. Just sort of holed up. It was a real tragedy, even though he offered other. But he came out here to New Mexico to a symposium like this one on alternative memory architectures, and gave this outline. I won't read, but it'll be in the slides. That why we're stuck in this von Neumann problem, and that we have all these computational elements, all these transistors that can change state billions of times a second are sitting there, but 99.99% of them are doing nothing. They're just waiting for these serial sets of instructions referring to specific addresses. It's a total waste, and all this hardware could be doing something totally different. And I think he arrived at an explanation of why things got so bad that's quite important. That why did we end up with all these recursive instruction sets? It's because even in 1950, the machines were faster than the programmers. So the only hope the programmers had of producing enough instructions to feed the machine was through recursive routines. And that's how we got stuck with all these recursive, whereas nature is not necessarily recursive in that way at all, and there are ways to connect the computation to the actual real universe in a way that you're not waiting for instructions, that you could do things totally differently. Why does the time have to be in the serial order? It should also be possible to trace backward or forward from results to causes through any path representation of the process. And what we've seen with some of this work that's being done using GPUs and FPGAs and so on are exactly doing what Bigelow dreamed of doing, where you're doing processing without waiting for specific addresses and instructions. So von Neumann would be very happy if he could see that you are finally escaping from his model that got named after him. So I'll leave you with three sort of last words from these three characters. From von Neumann himself: if the only demerit of the digital expansion system were its greater logical complexity, nature would not for this reason alone have rejected it. So he's just sort of waiting for the world to reject this, that everything had to be strictly digital, digitally coded. Ulam: what makes you so sure that mathematical logic corresponds to the way we think? Why are we continually trying to find the algorithms of the brain where it may be absolutely a non-logical process? It doesn't need to be logical. And Alan Turing himself: machines which are largely random in their construction in this way will be called unorganized machines. So he's essentially talking about neural nets. The machine is made up from a rather large number n of similar units and can behave in a very complicated manner when the number of units is large. This suggests that the cortex of the infant is an unorganized machine. So they had, at that time, the world they were working in was a matrix that was 32 bits by 32 bits by 40 bits deep. So that's 5 kilobytes of storage. That's all they had, and in that world they sort of imagined so much, and now it's open to do so much more with, thanks to all the people who give me access to these documents. My contact, if you send me an email there with nothing but one line of text, that's more memory than they had to work with. So quite a, thank you.